Okay. All right. Good morning, everyone. Welcome to the second lecture as part of this course. So yesterday we looked at conservation of mass. We derived an expression, right, for both for a compressible and for an incompressible fluid. Today we are going to look at rate of change of a property as we follow a fluid particle. Okay, so this is kind of in preparation to have essentially the momentum equations and the energy equation. Okay, so we are going to look at rate of change of a property of fluid as we follow a fluid particle. Okay. So, the statements of conservation of momentum and energy are applied for a fluid particle or for a finite fluid element. For what are they applied for? They are applied for a fluid particle, right? These are all the Newton's second law and the first law of thermodynamics, these are all applicable for a fluid particle or for a fluid of certain mass, right? So, essentially these are applicable for a fluid particle. Right. So, we said the rate of change of momentum of a fluid particle equals the resultant forces acting on the fluid particle, right. So, essentially we have to derive for a fluid particle. Now, let us think of a particular property of a fluid which we call it as represent with phi, okay, and this property is per unit mass, okay. Now, this property phi is of course a function of both the particle position, that is x, y, z, as well as time. Okay. So, we want to know how this property changes with time as we follow the fluid particle. Okay. So, we want to look at what is the total or substantial derivative of this property, that is d phi dt. Okay, we are going to represent with d phi dt. So, we want to calculate what is this quantity. Okay. So, because it is a function of both space and time, what would it be? It would be, what will be d phi dt, the substantial derivative? It will be rate of change with respect to time, partial phi partial t, right, plus if you apply the chain rule, what do we get? We have partial phi partial x, right, and then the position of the particle itself is changing with respect to time. So, this will be dx upon dt, right, plus partial phi partial y dy dt plus partial phi partial z dz dt, right. This is what we have for the substantial derivative. Now, we know that this fluid particle follows the flow, right. So, what would be the instantaneous derivatives of the position vector that we have here? What will be dx dt for this fluid particle? That will be the x component of velocity of the flow. So, this will be u. Similarly, dy dt would be v and dw dt would be, sorry, dz dt would be w, right. That is what we have. They essentially the time derivatives of these spatial coordinates of this fluid particle's position would be nothing but the instantaneous velocity vector. Okay. So, we are going to substitute back these three quantities into the substantial derivative definition. So, we are going to get d phi dt equals partial phi partial t plus for dx dt we have u, dy dt we have v and dz dt we have w. Okay. So, we are going to plug in these three quantities, that will be u partial phi partial x plus v partial phi partial y plus w partial phi partial z. Okay. So, we kind of got an expression here which we can kind of write in a compact notation using nabla. So, this will be partial phi partial t plus how can we write u partial phi partial x, v partial phi partial y, w partial phi partial z as? We could write it as the velocity vector, that is u bar, right, dotted with gradient of the scalar field phi. Okay, so this will be u bar dot grad phi, right? So that is your d phi dt. Okay. Okay. Now we have in the process developed an expression which is this part is the rate of change following a fluid particle, right, which we said is nothing but the rate of change. Okay, so this would be the local rate of change, right, and this would be the convection part of the change in phi. Okay, so this is the convection part. So we have now two expressions for the same quantity. On the left hand side, what we have, we call it as what? In what approach is this? We call this derivative that we have here. What do we call? Where do we use this derivative in? This is in a Lagrangian approach, right? Essentially, you are following the particles. So this is a Lagrangian description, right? Wherein you follow the particle. On the right hand side, what we have here, these two quantities, these describe the flow from an Eulerian approach, right? So this is an Eulerian approach where you are focusing on a certain quantity or a certain domain, right, a region of interest in the flow domain, and that is the Eulerian approach. Now, certainly all the governing equations that we have, the conservation of momentum and the conservation of energy, these are all defined in a Lagrangian approach, right. These are for a fluid particle. Now, of course, we can write and derive equations in a Lagrangian approach. However, the most common approach is the Eulerian approach when it comes to fluid mechanics. That is because our interest is in calculating the forces and the power developed by a certain region. For example, let's say you are interested in what will be the power required by a pump, or you are interested in what will be the power consumed by a furnace, or maybe you are interested in a lift that is produced by an aircraft wing, and so on, in which case your domain of interest is fixed. Okay, so in that sense, Eulerian approach is very much used, and that is what we are going to use in this part of the course. And of course, Lagrangian approach is also useful in certain calculations. For example, if you want to track the pollutants that are coming out of some plant, right, or if you want to kind of track, let's say, red blood cells in your body. So for all these things, you would use a Lagrangian approach, which would be much more convenient and straightforward. Okay. All right. Questions still here? You probably are already, aware of all these things. Okay. Let's move on. Okay. Now, just like the conservation of mass, right, where we said we derived the conservation of mass as partial rho partial t plus, what was the expression, plus we had del dot rho u bar, right, nabla dot rho u bar equals 0, right. We said there is a local change of density, right, and then we have net flow out of the fluid element that we have considered. These two together constitute 0, right, because the mass is conserved in this flow. Now, remember, this equation is developed per a unit mass or per a unit volume? This is developed per a unit volume, right. So we would be developing the momentum and the energy equations as well for a unit volume basis. Okay. Now, that means if I know that the rate of change of a fluid particle is, as I follow it, is d phi dt, right, this is the substantial derivative, this is per unit volume or per unit mass? This is per the unit mass, right, because phi, we said that this is a property per unit mass. Now I want to calculate it per unit volume. How do I do that? I just have to multiply with the density of the particle, right. Essentially I multiply with density. So this will be the rate of change of the property phi, right, per unit volume of this particle that we have considered. Okay. Now in order to develop this, we would consider, let me consider a similar to the earlier case, I want to consider a fluid element. Okay. Inside this fluid element, I am interested in the local increase of phi, okay, local rate of increase of phi, which is similar to the partial rho partial t that we have, okay. And we want to consider what will be the, I want to know what will be the net flow, essentially net flow of phi per unit volume out of the fluid element, okay. So, I want to consider these two quantities. One of them is the local rate of increase of the property phi per unit volume, and also the net flow essentially out of flow of phi out of the fluid element, okay. So, we want to consider these two, okay. So, this is certainly an Eulerian approach, right, as we discussed. Now, what will be this local rate of increase of phi per unit volume? That will be partial t times rho phi, right, because the instantaneous value of phi would be per unit volume would be rho phi, right, inside the fluid element, and then the local rate of increase is this much, plus what would be the net flow out of the fluid element of phi? What would that quantity be? We said, remember what was this quantity? Del dot rho u bar was the net flow rate, right? This was net flow rate out of the fluid element, right? We said if it is on the right hand side, it was net flow into the fluid element. You brought it to the left hand side, this is the net flow out of the fluid element, right? So, you have the divergence. So, what will be the net flow of the flow out of the fluid element? This would be del dot rho phi u bar, right? This would be the net flow out of the fluid element for quantity phi per unit volume basis, okay. So, we have this quantity. Now, I would like to expand this by considering rho and u bar together and phi to be together, okay. I have two quantities inside this divergence. I want to expand this. So, what will be partial t of rho phi? This will be rho partial phi partial t, right, plus phi partial rho partial t, okay, fine, plus I have del dot rho u bar phi, okay. I would write it like this as rho u bar dot. So, we are essentially expanding the divergence operator on this product of the scalar and a vector, right. So, essentially we have a del dot f times f bar, okay. So, we have this quantity which is where f little f is a scalar, f bar is a vector. So, my f bar is nothing but in this case rho u bar, and little f that I have is my phi, okay. We have these two, and then I am just expanding the identity, that is divergence of a operating on a product of vector and a scalar. So, this will be rho u bar dot grad phi, right, plus what else it would be? Phi times divergence of rho u bar, right. So, that will be the identity, okay. Now, if I collect the terms that are multiplied with the density and with phi, I have rho times partial phi partial t, plus I have this term here which is u bar dot grad phi, right, plus we have the remaining two terms are this guy and the last one here, okay. So, these are nothing but phi times partial rho partial t plus del dot rho u bar, okay. So, I kind of got two expressions, one multiplying the density, the other one multiplying the phi, okay. Now, what would be the value of this quantity that we have here? Partial rho partial t plus del dot rho u bar, that is 0 by virtue of the conservation of mass, okay. So, this is 0 owing to the conservation of mass, okay. Now, what is this quantity that we have here? Partial phi partial t plus u dot grad phi. This is the substantial derivative of phi, right. So, essentially this is rho times d phi dt, right, that is what we have, okay. That means we have just proved that the rate of change of phi per unit volume in a Lagrangian approach, that is given by this quantity, right, is nothing but is nothing but this, right. So, this is essentially the local increase of phi per unit volume and the net flow out of the fluid element of the phi per unit volume. Okay. So, what we have just derived is, okay, that is, okay. So, we said rho d phi dt equals partial t of rho phi plus divergence of rho phi u bar. Okay. So, this is what we started off with and we arrived at this expression, right. So, this is rate of increase of phi for a fluid particle, I am writing Fp, okay, that is as we follow the fluid particle equals the local increase or local rate of change of phi for a, I would write fluid element, okay, which is Fe plus we say the net flow rate of phi out of the fluid element. Okay. So, essentially we have considered a fluid element on the right hand side which is an Eulerian approach, and on the left hand side what we have is a rate of change of phi as we follow the fluid particle. So, this is Lagrangian approach. Okay. Okay. Question still here? No, this is all probably you have already learnt in fluid mechanics. Okay. Now, what about the sizes of this fluid element and the fluid particle? I just keep interchanging these two, right? What is that is in your mind about fluid element and a fluid particle? Yesterday we discussed that we are applying a continuum approach, and then this fluid particle we have taken is the smallest possible element, right, in the fluid, such that the molecular motions and the molecular structure can be ignored, right. That is what we discussed. Now, today we have this fluid element and fluid particle being interchanged. What would be the the size difference between these two? Like we have, I am conveniently kind of drawing this kind of a rectangular geometry, right, which I did not draw today, for a fluid element, right. For a fluid particle I never drew anything, right. So, what would be this sizes in terms of the comparison? They are of the same order of magnitude, right. So, whether we call it a fluid particle or a fluid element, they are of the same order of magnitude. Okay. We are still looking at a very infinitesimal small cube, right, for both of them. Only the thing is, in the first case we are riding with the particle, in the other case we are fixed in our reference frame, right, as far as the fluid element is concerned. Okay. All right. Now, now that we have derived this expression, it is very easy for us to write the three components of momentum equation, okay, and the energy equation, okay, by simply changing phi to assume u, v, w and e. Okay. So, where u, v, w are the three components of the velocity and e is the total energy that is stored in the fluid. Okay. So, because the momentum equation says that the rate of change of momentum as we follow the fluid particle, right. That is nothing but the three components would be like rate of change of momentum in the x direction as we follow the fluid particle. So, that would give you rho d u dt, right. We are essentially replacing phi with u. That would give you what in the Lagrangian approach? This will be partial t of, we just have to plug in instead of phi, we have to plug in u in both the terms on the right hand side as well as on the left hand side, right. So, essentially this gives us rho u, right, plus del dot, what do we have here? We have rho phi u bar. So, replace phi with u. So, this would be rho u bar. Okay. So, that would be your rate of change of momentum in the x direction for a fluid particle in the Lagrangian approach, right, as dictated by Newton's second law, and on the right hand side what we have is the same quantity in an Eulerian reference frame. Okay. Now similarly, the y component would be rho d v dt, right. So this is nothing but partial t rho v plus del dot rho v u bar, okay. That is your y component, and the z component is rho times dw dt equals partial t rho w plus del dot rho w u bar, okay. That is what we have, and for the energy equation, we have rho d E by dt equals partial t rho E plus del dot rho E u bar, okay. So we can simply obtain the rate of change term just by changing the replacing phi with either u, v, w, okay. All right. Okay, so we will move on to the momentum equation. Okay, so the momentum equation is, I would write it here, rate of change of momentum of a fluid particle equals the sum of forces or resultant of forces acting on the particle, okay, acting on fluid particle. So that is what we have. We have already derived what is on the left hand side, right, the rate of change of momentum we have already just derived. Now we have to look at what kind of forces that act on the fluid particle, okay. What are the forces that act on a fluid element? We can kind of categorize them into surface forces and body forces, right. What are the surface forces that you can think of? The stresses, right, this is shear stresses or the viscous stresses. So you have the viscous forces that are arising out of the viscous stresses, and then what else? Pressure, okay. So you have the pressure forces and the viscous forces, right, coming out of the pressure and the shear stresses that we have in the flow. What about the body forces? Sorry? Gravity, okay. What else? If you have a rotating domain or something, you would probably get a Coriolis force, right, or centrifugal forces, right, and so on, right. You can probably also have electromagnetic forces and so on, right. Anything that acts on the volume, you would call it as a body force, okay. Okay. Now we need to kind of understand these forces such that we can develop the right hand side that we have in the Newton's second law of motion, okay. So we look at the surface forces first, okay. So the surface forces arise out of the pressure and the viscous forces that we have, right. So this in order to know what kind of know the forces that act on it, we have to know what is the stress system that is a fluid element is subjected to, right. So we have pressure that is being acting on a fluid element, and we have shear stresses, right, or the viscous stresses. Those are the represented by tau ij, right. This is a stress tensor. This has 9 components, okay. Now what is the notation here? We say tau sub ij. What does I and j denote? I denotes the plane on which the stress is acting, okay. So this is the plane on which the stress is acting, and j denotes the direction, okay. So the direction is denoted by j, okay. And what about the sign convention? We consider a shear stress to be positive when, so the sign convention is tau ij is positive, right, when both the plane and direction are both positive or are both negative, right. So, essentially both the plane on which the stress is acting and the direction in which acting is, both of them should be either positive or both of them should be negative. Then we can call tau ij as a positive quantity, okay. If they have opposite signs, then tau ij would be negative, okay. So, for the purpose of this demonstration, this class, we would be only using, we will be kind of representing only the positive shear stresses on the fluid element, okay. Because the equations that we develop would not change even if you consider the other shear stress components, okay. It is just a easier thing to do, okay. And what about the pressure? In which direction does the pressure act on the fluid element? Pressure is always a compressive force, compressive, or is it tensile? It's always compressive, right? It always acts on the fluid element trying to compress the fluid, okay. So, let me consider a fluid element, okay. So, we consider a fluid element here now, where we would first represent the shear stresses that we have, okay. So, we have x, y, z, okay. Then let me first represent the normal stresses. So, this is tau x x, right. It is acting on a let us say on the x plane, right. This plane has a normal in the x direction and this is also acting in the positive x direction, okay. So, this is tau x x, and similarly tau y y would be this one, where this plane is a y plane, right, whose normal is in the y direction, positive y direction, and this is also acting in the positive y direction. And similarly we have the normal stress, the other normal stress is tau z z, right. This is also acting on the z plane and acting in the positive z direction, okay. Then we can go and look at the shear stresses, right. So, what about the other two shear stresses that act on this thing? Those are tau x y, right, that is this one, tau x y, and this would be tau x z, okay. And then here similarly we have tau y x acting on the y plane in the x direction. Similarly we have tau y z which is on the y plane acting in the z direction. Similarly we have tau z x and tau z y, okay. So, here all the normal stresses are represented in the blue and the shear stresses are all in red, okay. Now, these are all positive, right, okay. Now, if I were to draw a tau xx on the, let us say this face, on the west face, let us say if we call this as east face and this as west face, if I were to draw a tau xx as a positive shear, as a positive stress, in which direction should I draw it? Is it in the negative x direction or in the positive x direction? In the negative x direction, because it is acting on a negative x plane, right. So, it should be, so this tau xx would be a positive quantity, right, acting on a negative x plane in the negative x direction, okay. So, we would consider that for the derivation here, alright. Now, let me go and consider the forces, okay, in the x direction that are arising because of all the stresses that are acting in the x direction, okay. So, here for example, what are the stresses that are acting in the x direction? Tau xx is acting in x direction, which would give you a force in the x direction, right. What are the other stresses that are acting in the x direction on this fluid element? Tau zx, tau yx, right. Essentially, the second subscript should be x, right. All of them having a second subscript x will be acting in x direction and y in y direction and so on, okay. Then because the momentum equation has three components, I am going to write the first component, the x component first, and then we would kind of try to guess the other two components instead of deriving it all through again, okay. Alright. So, then let me redraw this same fluid element, okay, with only these three stresses, okay, tau xx, tau zx and tau yx. Now, all these three quantities are acting at the centroid of this fluid element, right. These are all acting at xyz, which is the centroid of the fluid element, okay. Now, we have to again use Taylor series expansion, okay, if we were to kind of draw them on the fluid element faces, okay. Here only to represent the state of stress, I have drawn it on the surfaces, but I will go back to my original fluid element, right, that we have used in the definition of the conservation of mass, okay. So, I am kind of redrawing this figure with our new or with our original way, that was where the shear stresses or the properties are all defined at the centroid. Okay, so this is the centroid which is XYZ, and I have tau XX defined at the centroid of this fluid element. Okay, so this is the fluid element. Then what would be its value on the east face? What would be its value on the east face? This would be tau XX plus, right, plus you are coming in the positive x direction, plus partial x tau XX, and we say that this fluid element has has delta x, delta y, delta z in the x, y, z directions as its length. So this would be dou partial x tau XX times delta x by 2, right, because we define tau XX at the centroid of this fluid element. Okay. Then in which direction would the tau XX on the west plane will act? It will act in this direction, right. This would be what? This would be tau XX minus partial x tau XX delta x by 2. Okay. So that is what we have here. What about the other quantities that we have? Tau Yx, right. So tau Yx would be acting in which direction on this north plane? On the north plane here, if it has to be positive, it has to act in the positive x direction, right, because this is a positive y plane. So this would be again tau Yx defined at the centroid. So this would be tau Yx plus partial y tau Yx delta y by 2, right. That is what we have here. Then I would draw a positive shear stress on the negative y plane here in the opposite direction, right, because this is a negative y. It is positive if it is acting in the negative x direction, right. So this is tau Yx minus partial y tau Yx delta y by 2, right. So that is the tau Yx stresses that we have on the north and south faces. What about tau Zx? It will be acting on the front and the back faces. So on the front face it will be acting in the positive x direction, right. So this is tau Zx plus partial z tau Zx delta z by 2, right, that is what we have. And on the negative side, so we have it here, which is tau Zx minus partial z tau Zx delta z by 2, right. Is that clear? Is that correct? Okay. So these are the three viscous stress components that we have drawn. We have left one more surface force pressure, right. We have left pressure. So in which direction does pressure act? So again pressure is defined as P at the centroid XYZ, right. What would be its value on this face? Again you have to use Taylor series expansion, and in which direction would it act? It would act in the negative x direction on this face. Okay, so this would be P plus partial x delta x by 2, and on the negative x face, on the west face, it would be acting in the, trying to compress it, right. It will act in the positive x direction. This would be P minus partial x delta x by 2, right. That is what we have. Essentially we have now 8 stress components, right, that we have kind of drawn, 2 per face, right. Now only these stresses can give rise to a force in the x direction, right. Okay. So now let us then calculate the force that would be arising because of this, right. So what will be that? If I consider the east face first, then we have or the west face first, then we have P minus, so if I consider this guy first, this would be P minus partial x delta x by 2 acting in the positive x direction, minus I have the tau xx, so this is tau xx minus dou tau xx by dou x delta x by 2, right. Both of these are acting on the west face, right. So this is the stress, this has to be multiplied with the area in order to obtain the force, and what would be the area? on which they are acting, that is this one, this is delta y times delta z, okay, that is delta y times delta z. So, if I multiply this with delta y delta z, okay, then what else I have? I have on the east face we have plus, okay, tau xx plus partial tau xx by partial x delta x by 2, right, acting in the positive. So, I have a positive here minus we have the pressure acting in the negative x direction, that will be P plus partial P partial x delta x by 2. Again this is also multiplied with delta y delta z, right, okay. Is that all? No, we have more terms, right, we have the other two terms which are nothing but on the y plane and the z planes, okay. So, on the y plane what is the other quantity we have? This is tau yx plus partial y tau yx times delta y by 2, okay, minus we have on the south face which is this one, what we have is tau yx minus partial y tau yx delta y by 2, okay, multiplied with what is the area? Delta x delta z, right, okay. And we have one more quantity, okay, I am going to kind of write it here, plus we have tau zx plus partial z tau zx delta z by 2 minus, right. So, that is this quantity, and then we have the tau zx minus blah blah blah, it is actually on the back face, right, acting in the negative x direction, okay. So, this would be minus tau zx minus dou by dou z tau zx delta z by 2 multiplied with area being delta x delta y, okay. Alright, good. So, these are the forces in the x direction that act on all the faces, on the east, west, north, south and front and back faces. This is forces arising out of the surface forces, okay. Alright, so what terms remain and what terms get cancelled here? Does P retain or P gets cancelled? P gets cancelled, okay, minus. What about tau xx? Gets cancelled, okay, you have a plus here, a minus here. What about tau yx? Gets cancelled. Tau zx also goes away, right. So, we have two halves of partial p partial x terms here and here, right, they sum up to 1, and similarly all other terms are also come in pairs, right, and they all sum up to 1, okay. So, what we have is as a result minus partial p partial x, right, multiplied by delta x delta y delta z, which I am not writing at the moment. Then we have plus, okay, this is a plus here, minus and minus, this is again partial tau xx by dou x, right, partial tau xx by partial x, again multiplied by delta x delta y delta z, and then we have plus another half here and a half here, that would be partial y tau yx, okay, plus we have partial z tau zx. All these quantities are multiplied with delta x delta y delta z, right, that is what we have, okay. Is that correct? Do you all see that? Alright. So, I can rewrite this as partial x of, I can club these two terms in the derivative terms of the x, which is minus p plus tau xx plus partial y tau yx plus partial z tau zx. So, if I write per unit volume, then I do not have to multiply with my volume of the fluid element anymore, okay. So, this is the force acting on the fluid element per unit volume, okay, in the x direction, okay. Now, will you be able to guess the corresponding terms for forces in the y and z directions? If I were to write, let us say y direction, what would that be? Partial x. So, because we are writing in the y direction, the second subscript has to be y, right? Second subscript has to be y. So, this will be partial x tau x y plus partial y. You would get the minus p, right, similar to the previous one, plus tau y y plus partial z tau z y, right. This is again per unit volume, this is the force that is acting on the fluid element in the y direction, okay. Now, what about z direction? Partial x tau, anybody? Tau x, xz, okay, xz, partial y, yz, partial z, minus p plus tau zz, okay. That is what we have for the force per unit volume in the z direction, okay, very good. Then we are now ready to write the momentum equation, okay. Usually it is customary to kind of group all the body forces as a source term on the right hand side, okay. So, essentially all the body forces we are going to represent them as a source term, okay, which is basically per unit volume, right. It has to have the same units as the other terms. So, whenever you have a source term, you have to represent as per unit volume, per unit time, right, because this is a rate equation, right. So, you have to have, so if I represent a source term with some s, okay, and if I write s sub m for representing source in the momentum equation, and we would use different subscript x, y, z to represent the source of the momentum equation in the x, y, z directions, then which is per unit volume, per unit time. Now, I can collate all of these things and write the final momentum equation in the x direction as what? Now, we are writing it for a fluid element, okay. So, what will be the rate of change of momentum for a fluid element that we have already derived that is nothing but the rho du dt, which we wrote it as partial t rho u plus del dot rho u bar, right. That is the rate of change of momentum equals partial x minus p plus tau xx plus partial y tau yx plus partial z tau zx plus, in addition we have this source which is momentum source, which constitutes all the body forces that are acting in the x direction, okay. Similarly, in the y direction we have rho dv dt equals partial t rho v plus del dot rho v u bar equals partial x tau xy plus partial y tau yy minus p plus partial z tau z y, right. That is what we have, plus smy, okay. Of course, you can also write the z momentum equation, okay. I would leave for you to complete later, okay. Questions till now? Anything on the momentum equation derivation? On the stresses? So, we have this body force, let us say we have a gravity force, okay. Gravity force acting on the fluid element, okay. For example, you have let us say acceleration due to gravity g bar is acting in the negative z direction, okay. This would be 0 minus g, okay. Then what would be your body force out of gravity? It would be rho g bar, right. So, in this context you would write your source term in the x direction as 0, source term in the y direction as 0 and the source term in the z direction as rho g with a minus, right. That is your body force if it is arising out of a gravitational force, okay. If it is not something else, then you have to kind of write these terms, the source terms, in a per unit volume, per unit time basis, okay. Okay, so essentially this kind of completes the derivation for momentum equation, okay. Then what we have next is the energy equation. So, what is the energy equation state? It says again the rate of change of energy of a fluid particle, right, equals net rate of heat added to the fluid particle plus net rate of work done on the fluid particle, right. So, that is how the rate of change of energy of a fluid particle is going to change, right. This is going to increase depending on if work is done on the fluid particle or if heat is added to the fluid particle, then its energy is going to increase, right. So, this is what we have. Now, of course, we have already derived the left hand side term, which is the rate of change of energy of a fluid particle, that is nothing but rho times d E dt, right. Now, we have to look at these two terms, the rate of net rate of heat added and net rate of work done on the fluid particles. So, the work done part, rate of work done can be calculated again from the surface forces that are acting on the fluid particles, and the net rate of heat added, that can be calculated from the temperature field, right, the gradients in temperature that we have in the fluid domain. Okay. So, we are going to take up these two in the next class. Okay.